All right, let's do this. Good news for everybody else that's still doing new stuff. Pretty much from here on out, everything we're going to do is kind of some review and minor extensions of things you've already done in your Algebra 2 course. So if you felt good in Algebra 2, this should come as a relief, and the topics should be relatively straightforward because these are things that we have done. There will be some minor extensions here and there. Look at some more situations that we didn't get a chance to look at in Algebra 2, but for the most part, this should feel pretty familiar, which is cool. Bless you. All right. So this first chapter that we're going to look at of review things is about exponential, logarithmic, and logistic functions. We've talked about exponential and logarithmic functions in your Algebra 2 course. We didn't talk about logistic things. That'll be a new thing here, but it's not like it's any big whoop. So let's kind of just start on exponential functions. So exponential functions can be written in the form a times b to the x, where a is not 0, b is greater than 0, and not equal to 1. So notice that in an exponential function, where is the independent variable located? In the exponent. That's kind of your defining characteristic of an exponential function. So why do you think that we require the a coefficient to be non-zero? What would happen if a was 0? It would just be y equals 0, which is a constant function and not something that we want to call an exponential function. That's technically a kind of linear function, right? Okay, straightforward there. Why do you suppose we require the b not to be 1? One to any power is just 1. So this would just simplify out to y equals a. Again, a constant function. Not interested in describing that as exponential. Why do you suppose we say that the b has to be positive? This one's a little sneakier. What would happen if what would happen if b is negative? What? What? Well, if the exponent was negative, it makes reciprocals, I think is what you're thinking. Jillian, what were you saying?
I was kind of along the same lines.
Okay. Yeah, so not that. So here's what to remember. So those values of x can be anything, right? Specifically, they could be fractions, like things like 1/2 or 1/4 or 1/6. What is the exponent of 1/2 the same as? A square root. And what happens when we square a negative? Imaginary results, right? We don't want something that's going to be outputting imaginary values for us. That's why we're requiring the b to be positive. Is that cool? And in fact, since the exponent can be anything and the fractions, they don't even have to be fractions, if we allowed the b value to be negative, you would have wicked discontinuity all throughout that thing at really unpredictable places. Like it would be just a bloody nightmare looking of a function. So it's a good thing that we don't allow that. So a little piece of vocab here. The a is often referred to as the initial value. The reason we say that is because f of 0 is just equal to a. And why do we know that? Because b to the 0 is 1, because we know anything other than 0 to the 0 power is 1. And we know that b can never be 0 because in an exponential function, b is always greater than 0. So it can't be 0. You know what I mean? And then we call the b value the base of our exponential. So just a little bit of vocab there. Everybody happy with that? So far, so good. Easy peasy. Let's run through a couple of examples of just evaluating some exponential functions. So if I wanted to do f of 2, what am I going to do? Plug 2 in for x. Come on, people. I know it's early, but... So I have negative 2 times 4 squared. Order of operations says, what should I do first? Square the 4. So I get negative 32. Everybody cool? As we already hinted at earlier, if I do f of 0, I should just get a. We kind of highlighted why that's true up above when we talked about why we call the a value the initial value. Is that okay with everybody? If I wanted to do f of negative 3, well, again, we plug negative 3 in for x. And then what is, and we know that we do the exponent first. So what is 4 to the negative 3? One over 4 to the third, very good. And 4 to the third is 64. So that gives me negative 1 over 32 when I reduce. So the exponent rule I used there was that negative exponents make a reciprocal. So I'm just going to kind of write down the exponent rule that we used along the way. It's just a nice little review. It's the main point of what we're doing. Everybody's cool? Again, these are exponent rules that we did in a lot of detail last year. I just want to hit on refreshing some of these because, well, things drift and they kind of, memories fade and all that. If I have f to the 1/2, or I'm sorry, f of 1/2, again, I'm going to plug 1/2 in for x. And as we hinted at just a moment ago, what is a fractional exponent going to be equal? Or in this case, the exponent of 1/2 is the same as a square root. So the rule that we're using there is that, and say if we have f of negative 3 over 2. So I would encourage you guys to think about this as that, since 3 times, or negative 3 times a half is the same thing as negative 3 over 2. The rule that I used to do that was that exponent of an exponent is the same thing as the product of the exponents. So 4 to the 1/2 is just 2, as we saw above. And then negative 2 times 1 over 2 to the 3rd. That's negative 2 times 1 over 8, which is negative 1/4. Any questions about any of these guys before we move on? No. So mostly the point of this was just kind of reviewing some of these exponent properties, since they'll creep in on this chapter and be useful again. As we go on, if we pull out any other exponent properties along the way, I'll do the same thing and just kind of re-quote the property to you that we're using. If you're confused on any of that, please let me know, but it's relatively straightforward. Let's do another example. So let's say that you're given a table of data and asked to find the exponential function that fits this data table. So this problem can be very easy or very hard depending on which points you're given. The best case scenario is one here where we have specifically given the x that is 0. Because immediately what this tells me is that the a value is 3. Since, again, what I'm looking to do is writing that kind of exponential equation. So if I know that where x is 0, it automatically gives me the a value right away. Everybody's cool with that? And that's wonderful, because now I can take any of these points and plug them in for x and f of x to solve for b. The point I would use is 115, because then I don't have to do any radicals. So if I divide both sides by 3, I just get b is equal to 5. So I have 3 times 5 to the x. Pretty easy, right? Everybody cool? Questions on this one? So let's say we want to write the exponential function h of x, and here we're given 2 points. Notice neither of them, the x-coordinate is 1. Or I'm sorry, is 0. Right? Notice neither in neither point the x-coordinate is 0. So we're still going to want to do the same thing. Our goal is to write an exponential equation. The catch is that we don't get either A or B for free. So we're going to have to write a system. So I'm going to write one equation using this point. So 48 is equal to A times B to the negative 3. And I'll write a second equation with this point, that 12 is equal to A times B to the negative 1. I'm going to call these equations A and B, and we're going to solve this system. Think back to your Algebra 2 class. What are some of the ways we talked about that we can solve a system of 2 equations? Oh, guys. Substitution. What's the other one? Elimination. Those would be the 2 primary algebraic methods we discussed. Either one of them is reasonable to do in this case. Personally, I like to do elimination. Now, this equation setup's a little bit different than the equations we solved in Algebra 2, because you notice that the 2 variables we're solving for are being multiplied rather than added. So when we do elimination, when the 2 variables are being multiplied, we're going to be dividing the 2 equations instead of subtracting. Okay with that? When I do that, the question is, should I do A divided by B or B divided by A? What I would choose to do is whichever one has the biggest exponent, I'm going to make that the numerator of my division problem. It doesn't really matter a whole lot, but it saves us like one step along the way to do it that way. So like, why not? Everybody's okay with what I've done there? So A divided by A, those just reduce out of there. 12 divided by 48 is 1/4. And then B to the negative 1 divided by B to the negative 3 is B to the negative 1 minus the negative 3. Or just B squared. Again, the property that I used there is that one, right? So to solve for B, we'll just square root both sides then. Normally, when I square root both sides, that creates a plus or minus, correct? Everybody's cool, right? However, B is the base for an exponential, so we know, what do we know about the base of an exponential? Has to be positive, so I'm just going to drop the negative possibility, and there's my value for B. Cool with that? I'm going to take that answer and plug it into one of the 2 equations. I'm going to choose to plug it into equation B. So now that I have my answers for A and B, I can write my equation. How's that seem? It's a little bit trickier there, but not so bad. Is everybody okay so far? Still doing fine? You stop me if I do anything that you're like, whoa, what is this? All right. So we've defined an exponential equation this way. And one of the vagaries of exponential functions is that, like, they're sometimes really difficult to compare two exponential functions because the base matters really a whole heck of a lot. One of the things we'd like to be able to do is to just kind of like pick a base and write all exponential functions with the same base. One of the most common ways we do that, or one of the most common bases we use when we do that, is the natural base, also known as Eulers number. We abbreviate this number with the letter E. This is the limit as x goes to infinity of 1 plus 1 over x to the x. And this comes out to be an irrational number. So what this means is that every exponential function f of x equals a times b to the x can be also written as f of x equals a times e to the kx, where again a is non-zero and k is non-zero. Basically what we're saying here is that we're going to find some exponent k such that b is the same as e to the k when we do this. Okay. So we have two different types of exponential functions. We have exponential growth, and exponential decay. So the growth is if the a value is positive and the b value is greater than 1, or if the a value is positive and the k value is greater than 0. Again, this would be for the a times bx equation. And this would be for the a times e to the kx version. And for decay, again, if a is positive and then b is between 0 and 1, or a is positive and k is less than 0, it's decay. And then if a is negative, it's just going to be the opposites. God bless you. So far, so good. No biggies so far. Yeah. Let's do some more examples here. Just let me pull this up because these are going to turn into story problems that I just don't want to copy down. Bless you. You got the case of the sneezies going today. I get it. All right. Got that. Copy that in. Whoa, that's small. We can do better than that. All right. So, given that a certain city has a population in 1990 of 782,248 people, and the population of the same city in 2000 is 895,193 people, and assuming the population growth is exponential, in what year will the population reach 1 million people? All right. So my first order of business here is going to be to write a exponential function to describe the situation. And really probably in this case, I'm going to call this t because the independent variable is going to be time. Should be pretty clear that the population of a city is going to depend on the time, since it takes people time to move in and have babies and die and all that kind of stuff, right? All right. So here's the neat little trick that I'm going to do. Right now it looks like I have 2 points, 1990, 782,000, yada, 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 and a second point of 2,000, 895,000, yada, 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 right? Which means I'd have to do that long solve the system process. Here's what I'm going to do. I'm just going to say 1990 is the same thing as year 0, which makes the year 2000 the same as year 10. By doing that, I can get the A value for free at 782,000, yada, yada, yada. And then to get my value for B, this becomes a much easier problem. Everybody cool? So I divide both sides by the 782,000. And then how am I going to get rid of that exponent of the 10 on the B? What cancels out an exponent of 10? 10th root, yep. And again, technically speaking, this would have a plus or minus attached to it because it's an even root. But we know that our answer is always just going to be positive, right? Because the B values have to be positive. So to type this into my calculator, what I'm going to do is I'm going to type in the number 10. I'm going to press the math button and go down to option 5. That lets me pick any root I want. That's why I typed the 10 in first. And then I'll just do my fraction command, 895,193 divided by 782,248. So there is 101 and change. Do that so I can see it. Everybody's cool with this and what we've done so far? So that's the first part of the problem we've accomplished. We now need to deal with the second part of the problem that asks, in what year will the population reach 1 million people? So what we're saying there is the output needs to be 1 million. Okay. Now notice the exponent is located, or I'm sorry, the variable is located in the exponent here. If we're trying to solve this algebraically, what tool are we going to have to use at some point to get that variable out of the exponent? You know the answer to this because we talked about it last year. Not a root, a logarithm. Have we talked about logarithms yet? No. So we're not going to use a logarithm yet to do this because we haven't introduced the idea of a logarithm yet. Instead, what we're going to do is we're just going to do this graphically with our calculator. So rather than typing this whole long number in again, I'm going to just store this as a variable. So I'm going to store it as the letter A. And then what I'm going to do in my calculator, in the left-hand side, I'm going to type in 1 million into y1. That's the left-hand side of my equation. In y2, I'm going to type in the right-hand side of my equation. And remember, I stored that number 101 in as A, so I didn't have to bother typing it back in. If you did type it back in, that's okay. Keep in mind, though, that like when I stored it as the letter A, I'm storing all the decimal places in the calculator's memory, not just the ones that are displayed. So I'm going to get a little bit more accurate answer than if you just typed in everything you could see. Everybody's okay still, though? All right. So now I'm going to reset my window because if I try to graph these two things, I'm probably not going to see the intersection because who knows what my window is set at. So the x's in this case are representing time. So in 10 years, my population went up about 100,000 to about 900,000, right? I'm going to assume it's going to take at least another 10 years to top up of 1 million, but I always want to make an overestimate, so I'm going to pick 30 years more, so from 0 to 30. By then, I'm quite confident that the population should be over 1 million. Does that make sense to you guys? What's the minimum population that my city should, or that I care about for my city? The Y's are representing the populations. What's the minimum population? The 782,000, right? I'm pick something a little less than that that's a round number, so I'll just do 750,000. And what's the biggest population I care about for the city? The 1 million, right? So I'm going to pick something a little bit bigger than 1 million. Again, I'll just pick a round number, so I'll do 1.25 million. Doesn't really matter as long as you can see the intersection. That's really all you need to worry about. So there's my 1 million line. Here's my population growth. Positive. Yeah, positive. Everybody's cool? Again, the window does not matter. All I need to be able to see is the intersection. right? So if you had picked different numbers than my window, as long as you can see the intersection, you're good to go. Yep. All right. How do I find the intersection on my calculator? I press second and trace, choose the intersect command. And since there's only two curves that I've plotted and they only intersect one time, I can just press enter 3 times. And there's my answer, about 18.2 years. But that wasn't what we were asked. It didn't ask how long. It said, in what year will the population reach 1 million? So what year does 18.2 mean? So remember, year 0 was 1990. So 18.2 should be year like 2008.2. But really, what should we say as our answer? Is during 2009. Right? At 2008, well, I mean, I guess we could say, right? In 2008, when it goes Jan 1, 2008, the population is still less than 1 million, right? The first year the population is over 1 million is 2009.
Doesn't it ask when it will reach, not when it is?
In what year will the population reach 1 million?
Isn't that like, that's still in the, you're still in the middle of 2008.
Are you taking a census every day in a city?
You don't take a census 2008, you take a census like every 10 years.
Oh my gosh.
Never mind.
Yeah, I mean, you can argue about this.
Confused.
Yeah, I think it's just one of these contexts of the questions. If you had said during 2008, I would probably let that go. Okay. If you wrote 2008, I would mark it wrong.
Gotcha.
Because in exactly 2008, it's not, the population is not 1 million. You know what I mean?
Yeah, I get what you're saying.
Yeah. So just like, you got to be a little bit careful about the question that's actually being asked and how you want to answer that. All right. Now, when we talk about populations, yes, sure. Alex, sure. When we talk about population, is an exponential function the best way to describe a population?
No.
Will a city keep on, let's take our same function here. And let's say, what would the population for the city be in, say, 2100? Right? So we're doing, I need Y2. So we're going to plug in 110 in, right? 110 years after 1990. So the city's population is at 782,000. We're saying the population then is going to be 3 million 120 years later. Does that seem realistic? Probably not, right? There's only so much area that you can build in a city. There's only so many services that you can provide or jobs you can provide inside of a city. It's pretty rare to get a city up in 3 million territory. Like, that's a monstrous growth of a city, right? And even more so if you go into nature, if you take a population of like an organism somewhere, is the population of, like some animal going to grow exponentially without bound? Of course not. There's going to be some upper bound where once we've kind of like filled up all the space and are utilizing all the resources available, there's eventually you're going to run out of food and everything, and you're not going to be able to your population won't keep growing. It'll kind of level off somewhere, right? So oftentimes what's going to be a more helpful function for us is a logistic function. So logistic functions are of the form f of x equals c over 1 plus a times b to the x. Or if you wanted to do this in terms of e's, it would be c over 1 plus a times e to the negative kx. So one nice part about these logistic functions is we have two horizontal asymptotes. So we have horizontal asymptotes at y equals 0 and at y equals c. So if we look at a logistic function, we have like asymptote at y equals 0, asymptote at y equals c, and your function is going to look like that, where it's kind of bounded in between those, which is a pretty good model for a population, right? Your population's never going to get less than 0. Yep, that makes sense. And it's going to be bounded at some place that's like a carrying capacity for your environment. Like, okay, at some point, like, we can't cram any more people into this city, or can't get any more rats living on this island, or whatever, you know, or any more disease in this cell, or virus in this cell, or whatever. So that's a pretty nice model for us. We have two types of logistic function. We have growth, like we've drawn here in blue, and we have decay that we've drawn there in green. For growth, that b value would be greater than 1, or the k value would be less than 0. For decay, the b value would be between 0 and 1, or the decay value would be greater than 0. Again, depending on which version of the logistic function you have. So let's do just a little light work with these logistics to get a handle on what's going on here. Okay, so let's say we want to find the y-intercept and the horizontal asymptotes for these functions. So how do I find the y-intercept for something? What's the x value for a y-intercept? 0. So I just need to do f of 0, right? So 0.6 to the 0 is 1. 3 times 1 is 1. 1 plus 3 is 4. So we have 10 over 4, or 2.5. Cool with that? One horizontal asymptote is always at 0. The other horizontal asymptote is always at c. And is this going to be growth or decay? So I need to be looking at the b value. Since that's between 0 and 1, this is growth. It's the opposite rule as for exponential functions, because where's the exponential part of the logistic located? In the denominator. So the rules are just reversed, right? The denominator gets really big, the number gets really small. Okay. So if we do the same thing for b then, g of 0 gives us 31 over 1 plus 4 times e to the negative 2 times 0. Negative 2 times 0 is 0. E to the 0 is 1. 4 times 1 is 4. Plus 1 is 5. So I have 31 over 5, or 6.2. Horizontal asymptotes are always at 0 and at C. And is this growth or decay? Since here the k value is 2, notice the formula has the negative sign in it for the logistic function. So the k value here is actually positive because the negative sign is part of the formula. Positive k would indicate decay for a logistic. And let's just take a look at the graph of these just to kind of see what's going on. Everybody still doing okay? Questions about any of this stuff we've done yet? Holler them out at me if you're getting, feeling wishy-washy about stuff or whatevs. Oops. Remember, to get the E, we press second and then the LN button. Okay. Then let's reset our window. We'll go negative 10 to 10 on the X. That seems fine. And then the Y will go 0 to 31 because I know that that's the, the top of the one of them. So here's the first logistic curve coming in. Okay, so that's 10 right there. There's the other one coming in. Oh, shoot. This is also growth, isn't it? How come nobody yelled at me? Right? Did I write that down wrong up here? Growth. Yes, I did. That would be why nobody yelled at me. Yeah. Boy, oh boy, Mr. Kulik. You really boogered this up. There. Now it's correct. My apologies profusely. Please make sure you update that part of your notes if you're writing things down. Now it's right. I promise. Blake. Of course. Yeep. You ever make a mistake, like when it's early in the morning and Blake's just perfect? That makes sense. That must be really convenient, right? All right. Last thing I want to do here today Got one more example with logistics, and we're going to be, I think, at a good place to stop. All right. So population of a city can be modeled using this logistic growth equation, where P is the population of the city in T years after 1950. At the beginning of what year will the city have 1 million people? Well, what are we asking to solve for? What year? So we're solving for T. Everybody's okay? So this 1 million must be what I'm going to plug in for P of T. Everybody's cool with how I set this up? So far, so good? How do you think I'm going to solve this? Graph it on my calculator. So 1 million, 1, 2, 3, 4, 5, 6 zeros. And then I'm going to use the fraction command for sure here. It's going to be a big mess if I don't. Okay. Now I'm going to set my window. So, again, T is years after 1950, so times 0 is going to represent 1950. I don't know how long this is really going to take. So, I don't know. I'm going to guess 100 years or something. It's a logistic function, so I know the lower bound is at 0. The upper bound is going to be the C value. Instead of typing that in exactly, I'm just going to round up to 1.5 million. And that should be good. Let's hit graph and see what we get. So here's my 1 million line. Here's my logistic function. I just barely got in there. But I did it. Second, trace, intersect command, enter, enter, enter. So I got the year, I got 79 for T. So 79 years after 1950. That is wrong page here all of a sudden. The year 2029. Actually, what does this say? At the beginning of, beginning of what year? Uh-oh. What should we say here? Yeah. Because 2029 won't quite be there, right? I know. Now you're on it.
Good.
This was better worded, I think, than the previous one. because they really specified the beginning of what year, right? Or better, we're a little careful, more careful. Carefuler, full of care. So I think we're going to stop here because I don't know, I'm pretty tired and I don't think that we need to keep going. So this, we can go through 16 is what we finished today. That was the first section. So that'll be the problem set that's due on the first, 5-1 will be part of that. Seniors, obviously, this doesn't include you.